Hi all, my name is Hashim Sharif. I work with Professor Vikram Adve at the University of Illinois, and the title of my talk is ApproxTuner, a compiler and runtime system for adaptive approximations. This work is done in collaboration with my colleagues that include Yifan Zhao, Maria Kotsifaku, Akash Kothari, Ben Schreiber, Elizabeth Wang, Yasmin Sarita, Nathan Zhao, Keo Joshi, Vikram Adve, Sasha Misailovich, and Sarita Adve. An important computing trend that motivates our work focused on approximate computing is the trend towards edge computing. Edge computing is a paradigm that brings the computation closer to the data where it is collected. Edge computing is now being deployed in a wide range of devices, including self driving cars, mobile phones, smart watches, virtual reality headsets, autonomous robots, among many other fields. Some advantages of computing at the edge include reducing latency by processing data in real time, reduces the network bandwidth usage, and it also helps reduce cloud and server costs. Edge computing also introduces a few challenges. The compute hardware on these devices is usually memory and compute constrained. Secondly, these are often battery powered devices like mobile phones, smartwatches, VR headsets, and so power and energy efficiency are key considerations in edge computing domains. Many different kinds of computations are being deployed on the edge, including machine learning tasks, image processing filters, data processing workloads, and signal processing, among many others. These applications are usually very compute intensive, which is a challenge since edge devices are usually compute constrained. An important opportunity is that many of these domains can tolerate small amounts of errors that introduce some acceptable degradation in the quality of the output result. Deep learning is a particularly common application domain on the edge and is a major focus of our work. Here I show a small convolutional neural network with three convolution operators. The network classifies inputs into different classes, and the quality of neural network predictions are measured by the inference accuracy metric. An opportunity here is to relax some amount of inference accuracy to achieve gains in performance. The resource we use to exploit this opportunity are approximations. Specifically, approximations are automatic transformation techniques or algorithmic variants that relax some accuracy to improve performance and or energy usage and or reduce the energy usage. For instance, one domain-specific approximation technique proposed in literature and also used in our work transforms convolutional filters to discard some subset of filter elements. This transformation reduces the amount of computation that need to be performed to compute the convolution output, and therefore it improves the performance with some loss in accuracy. Each tensor operation in this convolutional neural network, in more generally different subcomponents in a program, can potentially be mapped to one or more of different kinds of approximations. And for each approximation choice, there are usually multiple knob settings that impact both performance and accuracy. Because of this, tuning approximations for an application on a per operation basis creates a combinatorial explosion of approximation choices and knob settings as large as 10 to the power 74 in our benchmarks. This task of automatically selecting approximation knobs for each application component or operation is called approximation tuning. The goals of this tuning is to maximize performance and or energy efficiency while maintaining accuracy higher than a user given threshold. Now I'll show here the high level end-to-end workflow of ApproxTuner. The user provides a constraint on the acceptable quality of service degradation. For instance, in convolutional neural networks, user can say that they can tolerate up to 1 percentage point in a loss in inference accuracy. Then given a program with tensor computations, ApproxTuner chooses from a set of available approximation choices and maps each operator to either an approximate variant or leaves the operator unapproximated. For instance, the three convolutional operators shown here can be mapped to different approximation knobs. Instead of generating a single static mapping of knobs, ApproxTuner creates a trade-off curve of approximation configurations which is shipped with the program. While tuning a target program with approximations, ApproxTuner creates a set of configuration points on a 2D space with QoS loss or accuracy loss on one axis and speed up on the other. The configurations on the Pareto optimal frontier of this trade-off space are then selected to create a trade-off curve. If energy is of interest, ApproxTuner can also construct accuracy versus energy trade-off curves. A configuration has three attributes: a QoS loss, for instance, an accuracy loss, the speed up it provides, and the mapping of the approximation knobs to each tensor operation. The motivation for constructing this trade-off curve is to facilitate both install time and runtime tuning. At install time, different configurations can be picked from the curve and applied. For instance, a server machine with higher computational capability can pick the configuration with the highest quality of service, while a more compute constrained edge device may prefer a configuration that is computationally less expensive with possibly lower QoS. Also, the trade-off curve facilitates approximation tuning in scenarios where runtime conditions change, examples of which include low power modes in phones and battery conservation modes in robotics, to name a few such conditions. I'll take the low power mode example in edge devices to show how runtime approximation tuning can be helpful. When low power modes are activated, the system saves power by reducing the processor frequency, power gates a few compute cores, and other similar settings. Overall, these settings cause the system to slow down and affect the application performance. This graph here shows that as the power is reduced, the processing latency increases. Imagine the power is reduced to 5 watts from a high power mode of 10 watts. This would lead to a certain amount of slowdown, leading to a higher processing latency. The trade-off curve can then be used to pick an approximation configuration that provides the necessary speed up to counter this slowdown. If the slowdown becomes higher, possibly due to a further reduction in power, a different point from the curve can be picked, one that provides higher speed up with possibly more accuracy loss. The speed ups achieved by applying approximations allows for reducing the processing latency. Before I dive into the system details, a brief background on HPVM, which is the compiler system we build ApproxTuner on top of. As part of past work, we extended the HPVM compiler IR with high-level linear algebra tensor operations. Some of these operations include convolution, matrix multiplication, tensor reduce, among other commonly used tensor operations. The tensor operations enable the compiler and the runtime analyses in ApproxTuner to map these high-level operations to algorithmic variants. For instance, convolution operators can be substituted with approximate convolution implementations. The main contribution of ApproxTuner is a three-phase approach. This includes a development time phase, an install time phase, and a runtime phase. The first phase is a development time phase, which involves ahead of time tuning before shipping the program. In this tuning phase, the user provides an acceptable accuracy threshold and some calibration data to tune with. ApproxTuner supports tensor-based programs developed in either PyTorch, Keras, and HPVMC, which is a C extension for specifying HPVM data flow graphs. This phase then tunes the application for hardware-independent approximations. These are approximations whose impact on the output is fixed, regardless of the hardware used. Since object code portability is an important goal, this phase does not consider any hardware-specific options, which are then later considered in the install time phase. The development time tuning phase generates a trade-off curve with approximation configurations that are used in the install time and the runtime phases. After the program is shipped to the deployment device, the install time phase is invoked. The install time phase has two goals. Firstly, it refines the ship trade-off curve with real performance measurements, since the ship trade-off curve only uses heuristic estimates for performance speedup offered by each configuration. Secondly, it can optionally retune the program considering any additional hardware-specific approximations that are available on the target hardware platform. The refined trade-off curve is then used at runtime for dynamic approximation tuning. Another major contribution in ApproxTuner is that it combines domain-specific, generic, and hardware-specific approximations all in a unified framework. We support two domain-specific, two generic, and one hardware-specific approximation. The two domain-specific approximations apply to convolution operations. These are hardware-independent approximations that are applied in the development time tuning phase. The first is perforated convolutions, which is an approximation where a subset of the convolution outputs are computed and the rest are interpolated. Filter sampling is a variant of convolution that is computed using a subset of the input and the filter values. Both of these are existing techniques proposed in prior research. In our work, we redesigned these and developed efficient implementations for GPUs. The figures here show how perforated convolutions work. On the left is column-based perforation, where a subset of the tensor output columns are fully computed and some columns are skipped. The skipped columns shown here in red are then interpolated and computed as an average of the neighboring columns. Row perforation on the right similarly applies to rows. In both figures, 1 out of 3 rows or columns are skipped, and so the skip rate or perforation rate is 33%. Another knob is the start offset at which the rows or columns are skipped. For instance, in the left image, the perforation starts at the third row, so the start offset is 3. While in the right image, the perforation starts at the second row, so the offset is 2. The kind of perforation to apply, the perforation rate, and the start offset are all tunable parameters that are exposed to the tuner and tuned on a per operation basis. Similar knobs exist for other approximations, and these are detailed in the paper. We also support 2 generic approximations that are hardware independent and applied in the development time phase. Reduction sampling applies to reduction operations, with the reduction operation only using a subset of the inputs to compute. FP16 is another commonly used generic approximation that is used in a variety of application domains, including machine learning, graphics, among others. As the hardware-specific approximation, we also support mapping selected convolutions and matrix multiplications to an analog accelerator named Promise that provides configurable voltage swings. Promise supports a total of 7 knobs, with higher voltage knobs having higher energy consumption but low error, and low voltage knobs having low energy consumption but high error. We also propose a novel approximation tuning technique called predictive tuning that uses QoS and performance prediction models to make tuning more efficient. The motivation for developing an efficient tuning technique is that traditional empirical tuning is expensive. This is because auto tuning usually requires navigating and evaluating several thousand configurations. For instance, in our tuning experiments, we evaluated between 1,000 to 30,000 candidate configurations across different benchmarks. Moreover, for many benchmarks, empirically evaluating each configuration can be very expensive. We propose predictive tuning, which replaces the expensive empirical evaluation with models for predicting QoS and performance. For QoS prediction, the high-level idea is to measure the QoS impact of a single approximation applied to a single operation in the application and compose these individual QoS impacts to estimate the QoS for multiple approximations being simultaneously applied. For performance prediction, we use a simple additive model which computes the total execution time as a composition of the per operation execution times. Our predictive tuning strategy divides tuning into 2 phases. First is the QoS profile collection phase, and then an auto-tuning phase that tunes the program with QoS prediction models that use these QoS profiles. In the QoS profile collection phase, we collect a QoS profile for each approximation knob and tensor operation pair. Specifically, this means approximating a single operation with a particular approximation knob in isolation and measuring the QoS impact of the approximation knob on the end-to-end quality. We collect 2 different kinds of QoS profiles that I will describe later. Next is the auto-tuning phase that generates candidate configurations. In contrast to an empirical tuning workflow where the program binary is empirically evaluated each time, a QoS prediction model is invoked to evaluate the candidate configuration. The model uses individual QoS profiles from the profile collection phase and estimates the QoS for this candidate configuration. The predicted QoS is then sent as feedback back to the tuner so it can learn to navigate towards more profitable parts of the search space. If the model predicts that the QoS is higher than the user provided threshold, the QoS is further validated by empirical measurement to measure the real QoS. And then the configuration is selected as a valid configuration if the empirical measured QoS is higher than the user given threshold. The benefit of this approach is that only a subset of configurations need empirical evaluation. In the QoS profile collection phase, we gather 2 different QoS profiles. These profiles are collected such that a single operation is approximated at a time with a particular approximation knob. The first profile is a delta tensor profile that measures the deviations in the raw tensor outputs relative to the baseline tensor output. The baseline tensor output is the program's raw tensor output when no approximations are applied. The second kind of profile is a delta QoS profile that measures the deviations in the end-to-end QoS compared to the baseline. For instance, for neural networks, it would measure the loss in inference accuracy compared to the baseline with no approximations. These two different QoS profiles are then used with two different QoS models that predict the end-to-end QoS of a candidate configuration. Model 1 considers the delta tensor profile for each operation and knob pair in the configuration and sums up the tensor deviations. The QoS function is then applied after summing the tensor deviations into the baseline tensor output. Model 2 considers the delta QoS profile for each operation and knob pair in the configuration, sums up the end-to-end QoS losses for each, and subtracts this total loss from the baseline QoS. I'll now discuss the results for development time and install time tuning and discuss runtime tuning later. The hardware setup is a NVIDIA Jetson TX2 board with an ARM CPU and an NVIDIA GPU. For Promise, we use the simulator provided by its authors. For tensor operations mapped to the GPU and the CPU, we use direct hardware measurements. And for Promise, we invoke the simulator. For auto-tuning search, we use OpenTuner, which is an open source auto-tuner and search till convergence or a maximum of 30,000 iterations. The benchmarks we include are popular CNN benchmarks, including AlexNet, ResNet, VGG16, MobileNet. And the datasets we consider are MNIST, CFAR10, CFAR100, and ImageNet. Not all CNNs are evaluated on each dataset. Instead, different datasets are used with different CNNs. We also evaluate on an image processing benchmark that is discussed later. The baseline we compare against in all cases is a non-approximate version of the program running with FP32 precision. The tuning goal we consider is the degradation in the inference accuracy with three different thresholds. QoS lesser than 1%, meaning an additional 1 percentage point loss of accuracy is allowed. Similarly, QoS lesser than equal to 2% and QoS lesser than equal to 3%. This graph here shows the speedup achieved across the benchmarks when considering combinations of approximations, including sampling, perforation, and FP16 on the GPU. Overall, we see speedups ranging from 1.5x to 2.7x with a mean speedup of 2.1x with less than 1 percentage points of degradation in inference accuracy. Also, we see that by increasing the thresholds from 1, 2 to 3 percentage points, the maximum achievable speedup slightly increased for most of the benchmarks, since a higher allowable loss means more room for applying approximations. The energy reductions show very similar trends with a mean energy reduction of 2x with less than 1 percentage point loss in inference accuracy. We also evaluate if our predictive tuning strategy is comparable to empirical tuning in terms of achieving equivalent speedups. We also compare the two different predictive models. Predictive model 1 provides very comparable speedups to empirical tuning. Predictive model 2 provides relatively lower speedups, 1.97 compared to 2.27 provided by predictive model 1. Predictive model 2 is comparable to model 1 for most benchmarks, but for a few cases such as ResNet 18, AlexNet 2, and VGG16, we observe a significant difference in achieved speedup. This is because we find that predictive model 2 is less precise in predicting the end-to-end QoS loss. Predictive model 1 sums up the raw tensor outputs, so it captures the errors at a finer granularity than model 2, which sums up only the end-to-end QoS impacts. While the speedups and energy reductions with predictive tuning are comparable to empirical tuning, the reduction in analysis time is very significant. Predictive model 1 reduces the tuning times by 12.8x on average, and predictive model 2 reduces the tuning times by 20.4x on average. Predictive model 2 is faster since the model only sums up scalar values, while predictive model 1 combines the tensor outputs and is hence a little more expensive. The previous slide results show that predictive model 1 provides higher speedups. So in summary, these models provide a nice trade-off between efficient tuning times and analysis precision. Here I show the energy reductions when the Promise accelerator is considered for tuning along with GPU-based approximations. Across the benchmarks, the benefits increase significantly compared to only using the GPU, since Promise provides efficient support for convolutions and matrix multiplications. Overall, we observe a mean reduction of 4.7x with QoS lesser than equal to 3%. The speedups with predictive model 1 are very similar to empirical across all the benchmarks. As with GPU-based tuning shown earlier, predictive model 1 achieves higher speedups than predictive model 2. Here we show how the runtime approximation control works on an example program. In this HPVM program, the inputs are processed in batches and a runtime control is periodically invoked. The runtime control can switch the configuration based on a performance monitor that reports a slowdown. Assume the system detected a slowdown because it moved to a low power mode. To counteract the slowdown, the system then computes a target speedup, and the approximation configuration on the trade-off curve that provides that required speedup is then picked and applied. As conditions change, different points on the curve can be picked and applied. To evaluate our runtime tuning strategy, we perform an experiment where we vary the GPU frequency. We show here AlexNet, other CNNs have similar trends. The x-axis on the graph shows frequency with values lowering from left to right. The y-axis shows the normalized batch processing times. The blue line here shows that as frequency is lowered, the system slows down and the average processing time starts to increase. The green line here shows the accuracy. The line is flat because accuracy is unaffected when no approximations are applied. The red line here shows the batch processing times when dynamic tuning in ApproxTuner is enabled. The ApproxTuner dynamic control runtime uses the trade-off curve to pick configurations that counter the slowdowns imposed by the low frequency modes. The runtime tuning picks configurations that help maintain the same level of performance even when the frequency is further reduced. Also note that as frequency keeps reducing, the accuracy shown by the purple line here starts to gradually decrease since lower frequency modes require higher approximation levels to counter the higher slowdowns. The same behavior continues as frequency is further lowered, till the point that performance starts to slow down because approximations can no longer fully counter the slowdown. We also evaluate ApproxTuner on a combined CNN and image processing benchmark. The CNN classifies images into one of 10 classes, and only images belonging to certain classes are forwarded to an edge detection filter. The goals of this experiment are twofold. A, we want to show that ApproxTuner can tune components from multiple application domains in one application, and also that it can perform joint optimization for multiple QoS metrics. In this case, accuracy for the CNN component and PSNR for the image filter component. This graph shows how tuning for both thresholds can present interesting trade-offs. As the PSNR requirement for the image filter is lowered, while keeping the same accuracy constraint for the CNN, the speedups increase. Similarly, increasing the accuracy loss threshold while keeping the PSNR constant allows for higher speedups. And the highest speedups can be achieved when both constraints are relaxed. Depending on what combination of thresholds a user desires, a configuration from this trade-off space can be picked and applied. In summary, we presented ApproxTuner, an approximation tuning framework with three phases: development time, install time, and runtime. Our results on CNNs and an image processing benchmark showed between 1 to 2.7x speedup when only using GPU-based approximations. We showed that for two different QoS prediction models, our predictive tuning strategy is on average 13x and 20x faster compared to empirical tuning. We also showed that our runtime tuning helps maintain throughput in low frequency modes. We are currently working on releasing the ApproxTuner code and hope to open source it in the next 1 to 2 months.